Hello, this is a recording of the spring 2016 final. It's the first final that I'm going through, so we'll see how it goes. But pretty excited. This is essentially the easiest one, which is why I'm doing it first. But shouldn't take too long, and let's get going. So, question one: we want the equation for a line that passes through this point and is parallel to this line. So whenever we see something like this, we know that we want to have the same slope, so the same coefficients on t as the x, y, and z components of the line that we're given, and we know that we need to contain 1, 2, and negative 3. So the way I always set it up is kind of in this notation I learned in high school. So we know we want to pass through 1, 2, 3, so we're going to put 1, 2, negative 3. We know we need to pass through that, and we know that we want to have the same slope, so the same change per unit t as the line given. So that'll be 2, negative 1, 3. And so this is our new line. And we can expand this out, and one of the answer choices, well, all these answer choices are expanded, but if you see, we can expand this to like x equals 1 plus 2t, or y equals 2 minus t, that kind of thing. And so really you can see all we've done is drop the constants here and added our new constants from up there. But if we go through and look for answer choices, let's set up that first one that we had, x equals 1 plus 2t. Let's cancel out everything that doesn't have 1 plus 2t. And it's everything, and we have our answer. Let's just make sure with the other choices, with y and z, we said y equals 2 minus t, which is right there, and z equals 3t minus 3, which, yes, exactly. Okay, got a little confused there, but 3t minus 3 is exactly there, and we are good. Question 2, find the equation of the plane that contains this point and this line. So this one's a little weirder, but really what we need, because we know that the plane is defined by its normal vector, we're given this point, and we know that there's a line that's just making its way on by. We can find 2 points on this line and have position vectors from this given point to these points on the line. And then if we take the cross product, we know that that will give us the equation, or sorry, the vector that is normal to both of these vectors, which, since we know that all 3 of these points lie in the plane, the vector that we get will be the vector that defines the coefficients of the plane. So let's do that. Let's set t equal to 0. We get 1, 2, 3 as a point that is on this line, and let's set t equal to 1, and we get 4, 3, 4. But these are just these are points with respect to the origin. Let's make them points with respect to our given point right here. So pretty much all we're doing is seeing how we have to travel from this point 2, 1, 1 to get to 1, 2, 3, which is going to be, we got to go 1 unit down to get to -1. We got to go 1 unit up. We got to go 2 units up. And then for this guy, we need to go 2 units up, 2 units up, and 3 units up. That's just how I think of it. I know there's some, you can set up a subtraction and get the same thing out, but I like to do that. So now we've got these two, and we can take our cross product, and we should get our coefficients of our plane. So our first cross will be -1. Our second cross will be 7, and our third cross will be -4. And importantly, so we see that we only have 1, 7 in here, and that this is our correct answer. But why are all of our coefficients flipped? You see, we got -1, 7, -4, and they got 1, -7, 4. But importantly, it's important to realize they do this sometimes. Find an equation of the plane. So this actually does satisfy things. If we take this over here and make -x plus 7y minus 4z, and we plug in 2, 1, 1, which is we know to be a point that is on the plane, we will get -2 plus 7 minus 4, which is 1. And you can see how inverting all of the signs in our equation, or rearranging it, will give us answer choice C. Okay, question 3. What is the x-coordinate of the point where the curve defined by 2t, comma t minus 1, comma 1 intersects this given cone? So this is actually a lot less. This is if you haven't really worked on any of this stuff since exam 1, this might take a little bit of memory jogging, but it's really not that bad, because all we have to do is for every if we take this to be all of our x values, this to be our y values, and this to be our z values, we can take these guys, plug them in over here, and we will get the value t for which the intersection is true. So plugging in 1 for z squared, we get 1 equals x squared, where x is 2x, so we get 4x squared, plus y squared, where y is t minus 1, so we're going to get plus t squared minus 2t plus 1. Our 1's will cancel. Oh, I wrote x here, didn't I? That is a t. We can, let's see, let's make sure I don't want to make sure, I want to make sure I didn't mess anything up. Yep, so we can cancel these, place this with a t, equal to 0, and let's factor out a t. We will, oh sorry, no. 0 equals 5t squared minus 2t, and then we can solve this. 2t equals 5t squared, 2 equals 5t, 2 over 5 equals t. That's not a t. And you might be a little hasty and just go and choose B, because it seems like we've come to a pretty clear answer, but they're asking for the x-coordinate of the point where this intersection occurs. And since we know that t is equal to 5, we can just plug t into 2t, which we know to be our x value, and we get 4/5, which is our answer. Okay, we have a 3D limit question. These are actually pretty rare to see on the final, but this is a relatively easy one. They want us to find two limits. One, they're calling M, which is the limit, let's see, which is the limit along the line y equals x. So every x will substitute with a y, or every y will substitute with an x. We'll get the same answer either way. And another one that they're calling L, which is approaching along the x-axis, which is really approaching along y equals 0. And so keeping our formatting nice, all we need to do is plug these in, and our answers will pop out. There's no special math that we need to do. So for y equals x, this f of x will be 3x squared. I'm just substituting x in for every y, plus x squared over x squared plus x squared, which will simplify down to 4x squared over 2x squared, which is 2. So we know that m is equal to 2. That lets us bring it down to a 50-50. Then, as far as L goes, if we set every y equal to 0, we'll get 3x squared plus 0 over x squared plus 0, which is 3x squared over x squared, which is 3. And we have our answer. Okay, the equation of the tangent plane to this surface at the point 1, 3 for x and y is what we're trying to find here. And we know that our tangent plane is made, in this case, is z minus z naught equals zx, x minus, x naught plus zy, y minus why not? Where zx and zy are the partial derivatives of z with the values x and y plugged in to get their respective derivatives. So we can solve this pretty easily. Let's get z naught first, because that should be the easiest part. Z equals e to the x squared is going to be 1 plus 3 squared is going to be 9 minus 10. So this is e to the 0, which is equal to 1. So z minus 1 is, okay, now we got to find zx and zy, because we know that, let's just put these in as replacements. We know that x naught is 1, because that's the point that we're dealing with. X minus 1 plus zy, y minus 3, because that's our other piece of our ordered pair. Okay, so zx is just going to be our partial derivative with respect to x, which is going to be 2x e to the x squared plus y squared minus 10, whereas zy is going to be 2y e to the x squared plus y squared minus 10. We know that all of these e to the x squared plus y squared minus 10s are going to be equal to 1, and so 2x, where x is equal to 1, is just 2, and this whole thing is just equal to 2, whereas this whole thing will just be equal to 6. So now we can make a little more space and do some replacing. So we know that zx is 2 and zy is 6, and now we can solve. So z minus 1 equals 2x minus 2 plus 6y minus 18. Okay, adding 1 to each side, because we see that our answers are all in terms of z equals over here, we will get minus 19. And z equals 2x plus 6y minus 19 is an answer choice. Okay, question 6, we have a multivariable chain rule question to deal with. We know that for this, we're looking for the partial derivative of f with respect to v, where f is composed of x and y are composed of u and v. So we know that partial f partial v is going to be equal to partial x, partial f partial x times partial f v, and then we need to add partial f partial y multiplied by partial y partial v. And that should be our answer. Now we just have to put everything together. So let's remake our equation so we can start adding things in as we go, and let's start solving. So fx, which is partial f partial x, is just going to be 8x to the 7th y squared, and fy is just going to be x to the 8th, well, 2x to the 8th times y. Let's figure out what x and y are, which should be pretty useful for us. We see that x is 12u plus 2v, where u is 1/6 and v is pi. So x is going to be 2 plus 2 pi, whereas y, which is sine uv, is going to be sine of pi over 6, which is 1/2. So we can solve these guys right off the bat. So 2 plus 2 pi, oh, I'm in a room late at night and the light just turned off because I'm not moving or making that much noise. Oh, that's great. Okay. It's not that dark. Okay, so we see that they're leaving 2 plus 2 pi in that form in all of the answers. So we'll just leave it like that too. So fx is going to be 8 times 2 plus 2 pi to the 7th, and then we need to multiply by y squared, which is going to be 1/4. And then this is still multiplied by partial x, partial v, and then we are adding let's see, Fy is going to be 2 times 2 plus 2 pi to the 8th times 1/2. So cleaning everything up a little bit, this is going to be 2, and this is going to be a 1. And we're still multiplying this by partial y, partial v. Okay, so now we need our partial y and partial v. So, we need our partial x, partial v, and our partial y, partial v. So xv is just going to be 2, and yv is going to be u cosine uv. And so solving 2, plugging in negative 1/6 and pi is just going to be equal to 2, whereas this over here is going to be root 3 over 12. And finally, putting everything together, root 3 over 12 goes here, and 1/2 goes here. Oh, sorry, I read the wrong one. 2 goes here. So we're going to get 4 times the quantity 2 plus 2 pi to the 7th plus root 3 over 12 quantity 2 plus 2 pi to the 8th. And we see that that is one of our options. Okay, question 7, we're using implicit differentiation here to compute dy, or partial y, partial x. Well, I don't know what their notation's doing there. Okay, but we do know how to do this. We have a nice formula, and our formula, if we want dy dx, we need to take negative partial x, let's call this function, I'm overcomplicating things. So we need the partial derivative with respect to x, and that is divided by the partial derivative with respect to y. And we know that this guy will be equal to that. So let's set this thing up. What is our partial derivative with respect to x? Well, that's just going to be 2xy cubed plus 3yx squared, just treating y as a constant. So we'll grab this and stick it right in there. And then partial y is going to be 3x squared y squared plus x cubed. So now all we have to do is plug in. But before we even do that, just to make sure we don't mess up later, we see that we're only plugging in positive values, and there are no there's only one negative value in our expression over here. So our answer has to be negative, and so we can cross off those two. But let's go plug in just to make sure. So plugging in 1, 2, we will get negative 16 plus 6. Nope, 16 plus, 16 plus 6 over 12. Whoops. It's that time of the night. I cannot do basic math. Oh, yeah, 12 plus 1, sorry, and there's our answer, because this is going to be negative 22, and 12 plus 1, I'm still pretty sure is 13. Okay, question 8. How many critical points does this guy have? We know that critical points will occur when both fx and fy are equal to 0. So we need to solve for both those partial derivatives and figure that thing out. So fx is going to be 6y squared minus 6x squared, whereas fy is going to be 12xy minus 12y cubed. Yes, okay. So solving and simplifying a little bit, we see that this thing is the same thing as 6y squared minus x squared equals 0, which is the same thing as saying y squared equals x squared. So this is a condition that must be true. We also can go down here and pull out a 12y, and 12yx minus y squared has to be equal to 0. We can divide by 12y and see that our other condition is that x has to equal y squared. So where are points where this is true? Well, 0, 0 satisfies both of these. And what if x is 1? Well, if x is 1, y can be positive 1 or negative 1. So 1 comma 1 and 1 comma negative 1 both work. What if x is negative? Well, if x is negative, there's no value that we can square in here that will make that hold. So as it turns out, these are our only 3. Okay, let's see. It looks like we have a pretty basic rectangular derivative. Oh God, integral, rectangular double integral to do. So let's draw that out. Let's sketch it. We're bounded by y equals 0. So the x-axis, and x equals y squared, which is just our square root curve, which is x equals y squared, and x plus y equals 2, which is the same thing as 2 minus x. So 2 minus x. And then we're looking at this area here. So if we're setting up our integral with y in our integrand, it'll be much easier if we integrate with respect to x first, because we'll be hitting the two kind of dynamic boundaries, whereas if we went up through y first, there'd be kind of two choices. We could either exit through this guy or exit through this guy, and we want to avoid those kind of edge cases. So let's set this up. If we draw a line parallel to the x-axis, the curve that we'll hit first is x equals y squared, and then second we will hit the curve x equals 2 minus y, and then this is dx. And as far as y goes, we know that the minimum bound for y is 0, as stated right here, and the maximum bound will be the intersection here of our functions, x equals y squared and x plus y equals 2. So setting those equal by the fact that there's an x in each of them, we can replace x with y squared. Just plop that guy in there, and we get y plus x squared. Nope, not that either. Not that either. Y squared plus y equals 2. We can subtract a 2 over and factor this thing, and we will get y squared plus y minus 2 equals 0, which is y plus 2 and y minus 1. And we only want the positive roots, because obviously we're only looking for positive y values because y is bounded below by y equals 0. So as it turns out, this is y equals 1, because this guy is a negative root and we don't care. So dy. So now we can finally solve, and solving this first guy, because it's not dependent on x, we'll just end up multiplying by this and subtracting the product of that. So doing that, we'll get 2y minus y squared minus y cubed, and then integrating, we'll get y squared minus y cubed over 3 minus y to the 4th over 4, evaluated on 0 to 1. And this is 1 minus 1/3, 1 minus 1/3 minus 1/4. And we can put all this in twelfths to get a real answer out of it. This will be 12 over 12 minus 4 over 12 minus 3 over 12, which is 12 minus 7 over 12, which is 5 over 12. Okay, the volume of the region below this graph and above that graph. Okay, so it looks like we're going to be dealing with a cylindrical integral because we have z equals, and all this stuff is symmetric about the z-axis. Before we do anything, let's go replace stuff with r, because that makes it a little easier to deal with. So this is z equals 16 minus r squared, whereas this is z equals 3r squared. And if we were to graph these, this they'd both be cones. This one, um, yeah, this one would be a much sharper cone, this guy, whereas this guy would be a downward facing kind of more flat cone, and we're looking for this volume in here. And we see that this guy will be our upper bound and this guy will be our lower bound. And you can always really tell with these whichever has the largest constant, because when r is equal to 0, it's that z equals that constant value that will determine which is above which. So we can set this integral up pretty easily, although we do need an r value. So we know that dz, for z, it's going to run between 3r squared and 16 minus r squared. But then, importantly, we still don't know what r is equal to, but we can set these guys equal to each other to see what this maximum radius r is. So setting them equal to each other and subtracting an r squared over, we'll get 16 equals 4r squared, which is 4 equals r squared. So r is 2 at its maximum. So r runs between 0 and 2, and we're not dependent on theta at all. So 2 pi goes outside. And of course, we need an r in our integrand. So doing the same thing, we're not dependent on z, so we can just multiply in, but subtracting this guy, and we will get 16r minus r cubed minus 3r cubed. 3r cubed, which is 16r minus 4r cubed, and then integrating this on 0 to 2 dr, we will get 8r squared minus r to the 4th on 0 to 2, which is going to be equal to 32 minus 16, which is 16, multiplied by our 2 pi that we had lurking out here, and we get 32. Find the formulas for a and b that convert the triple integral from rectangular coordinates to spherical coordinates. Okay, so we're looking for what our integrand is going to turn into, and we're looking for what our lower bound on phi is going to turn into when we convert this guy over. So let's start with our integrand first. We know that for a spherical integral, we're always going to have a p squared sine phi, and then x in spherical coordinates is I'm saying p, sorry, rho. It's going to be rho cosine of theta sine phi. And so if we look around, we're looking for, rho cubed sine squared phi cosine theta, which we see here and nowhere else. So these three are automatically out. Okay, moving on, we see that we are bounded, z is bounded on the bottom by the xy plane. So if we graph this thing really quickly, z is bounded by 0, and on the top by the cone z equals r, which is just going to go out at 45-degree angles here and all the way around. And so we're actually looking at this volume in between where it's looking like, so we have everything we need to solve this now, because we're looking for our phi bounds. We know that our upper phi bound, just like we looked at here, is going to be pi over 2, but our lower phi bound we just found is going to be pi over 4, because all of this area inside here we are not counting, but we're counting all of the volume that's outside it all the way around. So our lower bound on phi needs to be pi over 4, and there's our answer. Okay, let E be the region in the first octant that is outside of this sphere and bounded by these guys. I actually did this question earlier today, and I'm really, really sick of spherical integration at this point, but we'll do it anyway. So setting this up, making a little graph, because this one is kind of necessary for. We are looking at a sphere that's bounded by y equals 0. If this is x, y, z, y equals 0 is just the xz plane, z equals 0, which is the xy plane, and y equals x, which is just a plane. That's really ugly. A plane that's just running through here. And so we see that if we're dealing with a radius of 1, we're dealing with kind of this sliver of sphere, well, really hemisphere, right in there. So because it's y equals x, we know that it's cutting this this 90-degree angle equally in half, so that's going to be a 45-degree angle. And we know that 45 translates to pi over 4 in radians. So if we move everything over a little bit, we can set up this entire integral. We know that rho is running between 0 and 1. We know that our integrand has a z in it. So it's going to be rho cubed sine phi cosine phi d rho d phi. Well, what's phi running between? Phi is starting at the z-axis, so 0, and running all the way down to pi over 2. And what's theta doing? Well, theta is only going from 0 to pi over 4, like we just established. So since we're not dependent on theta, we can multiply by pi over 4 outside here. Now, integrating rho to the 4th over 4 on 0 to 1, well, that's just going to be equal to 1/4. So we can get rid of all of this and put a 1/4 in there. And we know that we can substitute sine something, cosine something for sine 2 something. I'm sorry. We got to have 2 of these guys. So we can substitute sine phi cosine phi for sine 2 phi over 2. So this is the same as 1/8 sine 2 phi, which we can integrate much easier. So integrating, we will get negative 1/16 cosine 2 phi, which when we integrate on 0 to pi over 2 will give us 1/16 and negative 1/16, which is 1/8 multiplying by our 1/4 that we had sitting out here will be pi over 32. Let me just quickly make sure. 12b. Good. Last thing I want to do is figure out that I did the explanation wrong in 2 different videos that are already uploaded. Okay, so we have a parametrized surface, r of u and v, in terms of u and v, and we need a vector normal. So note that they're not saying the vector. That's a good hint that we should be open to some changes later on. So we know that the normal vector is going to be RU cross RV, where RU and RV are the partial derivatives of R with respect to either U or V. So RU is going to be 1, 0, 2UV, whereas RV is going to be 0, 1, U squared. And we are at 1, 2, 2, so instead of keeping the U's and the V's around, especially with my handwriting, it's much more useful to just get rid of that and plug in. So now we can solve. So taking our cross product, we get -4, -1, and 1. And we look at this and we look at our answer choices, and ours isn't up there, but they want a vector normal. Remember that we have 2 normal vectors. Let's say this isn't a plane, but let's say we just had a plane sitting here. We have a normal vector coming up out of the plane, and we also have a normal vector coming going down out of the plane. And we found one of them, and our answer choice is the other one, which is just the sign flipped version. Okay, let f be a scalar function, and f be a vector field in R3. Which of the following expressions are meaningful? So this problem really bugged me until I figured out where I was being dumb. So let's go through it. Okay, operations that we can do on vector fields. Well, we can take a curl of f. We can take the divergence of f. And at least for our our purposes, that's it. As far as potential functions, so scalar functions go, we can take gradients. So just taking a look at our options here, can we take a gradient of a vector field? No, we can only take a gradient of a scalar function. So that's no good. Can we take the divergence of a potential or scalar function? No, we can only do that to a vector field. So that's also out. Can we take the, this is the one that really bugged me, the curl of the divergence of f. So a nice little factoid, the divergence of the curl of f is always 0. But the curl of the divergence of f isn't even 0 because it doesn't make sense. The reason it doesn't make sense is what you get when you take a divergence is a scalar function. Because you're taking a dot product, you're doing del dot f, so you're going to end up, you're adding everything together in the end. You're going to end up with a scalar function. And when we can't curl a scalar function, so that's no good. And then right here, we already said gradient of f was good, and we can cross with this would be a vector field here. So we can do a cross product there, and curl of f, yeah, we can do that. And so 2 and 4 is our answer. Okay, 15, we're finding a potential function such that the gradient of the potential function is a vector field where that vector field is yz, xz, xy. Oops. And use it to compute a line integral f dot dr. So none of this matters because we know that we can apply the fundamental theorem of line integrals, which says that if we're in a conservative vector field, the path that we take does not matter. All we have to do is take our end state and subtract our starting state. And what these end states and starting states are is just plugging our x, y, and z values into our potential function f. So we got to find that potential function f. They tell us it exists, but what we have to do is take some antiderivatives here and see what pops out. So let's do that. We'll take an antiderivative with respect to x. That's an f dx. We want integral dx, integral dy, integral dz. And when we do that, we will get xyz, comma, xyz, comma, xyz. And, we have full overlap here. The only function that we could pull out of all of this, that when you take the gradient of it gives you this, is just xyz. And in general, all overlap cancels out, and you only count one of them. This is the weird way I do this. I know there's a better way, but that's not what I just started doing. So if you've got your own way, please don't change. I'm sure mine is worse. Okay, so we know that our potential function f is xyz, and we know that our curve is defined. Let's make an r of t, where r of t is t cubed 1 plus t squared 1 plus t squared, and where this is just coming from our x, y, and z values over here, where 0 is less than or equal to t, which is less than or equal to 1. So we can pull out our x, y, and z values for our start and end states right from here. So plugging in 0, r of 0 is going to be 0, 1, 1, and then plugging in plugging in r of 1, we're going to get 1, 2, 4. Okay, so evaluating at our end state here and subtracting our start state, well, we have a 0, so our start state is going to be 0. and our end state is going to be 8. 8 minus 0 is 8. Okay, we have a vector field which is defined in terms of ij and k, and we're just finding the curl. So we know that curl of f is going to be the del operator crossed with f, where the del operator is just, in this case, it's just a vector, which is partial x, partial y, partial z. And we are crossing this, I'm going to bad with the space management. We're crossing this with 2y plus 2z, z plus x, and x plus y. And so taking this cross product, we will get 1 minus 1, comma, 2 minus 1, comma, 1 minus 2. So we will end up with 1 minus 2. There we go. We'll end up with 0, comma 1, comma negative 1. And just because I don't trust my crossing this late at night, 16 is D. Okay, 17. S is this portion of the cone, and we're looking for the surface area of S from 0 to 1 on Z. So we can find this pretty easily. We know that this kind of surface integral, that ds will just be replaced with the square root of zx squared plus zy squared plus 1. And so we can compute that. Zx is going to be x over root x squared plus y squared, whereas zy is going to be y over root x squared plus y squared. So this is actually really, really satisfying how all of this works out, because this square root, we make it nice and big, is going to be x squared over, if we square these denominators, it'll be x squared plus y squared over x squared plus y squared plus 1. And then, of course, we can add a y squared over here because we have like denominators, and all of this simplifies down to 1, and 1 plus 1 is just going to be root 2. So that has turned this integral into what is now just an integral over the xy plane projection in 2 dimensions of the surface. And so we can make a double integral. Root 2, we have a z in here, but we can replace our z with x squared plus y squared to the 1/2. Root x squared plus y squared. And, well, we're a cone, and we're going between 0 and 1, and so the xy projection is just going to be a circle with radius 1. And that makes polar integration pretty easy here. We can replace this with an r, and then we add our r that's sitting there in the polar integral waiting already. dr d theta, we know that theta has to run from 0 to 2 pi, and that r has to run from 0 to 1. So integrating, we will get root 2 r cubed over 3 on 0 to 1, which is just going to be root 2 over 3 times 2 pi, which is 2 root 2 pi over 3. Okay, so we are solving here for f dot n ds, which is going to be a flux integral. You can use the divergence theorem here, but only because we have a solid cylinder, but we don't even need to, because f dot n is something that we can totally solve for right here, because we're pretty much just given constants. The only leap is to realize that, so we have this cylinder, and we have a plane cutting that cylinder in some way. And what is the normal vector of the surface in here? Well, it's just going to be the coefficients of the plane, which define, because a plane is defined by its normal vector. So if we pull that out, we will get 2, 1, -1, but they want an upward pointing normal vector, so we need positive z, so this will be -2, -1, 1. So that's n. That's our normal vector. But what about f? Well, f is just 1, 2, 1. So -2, -1, 1, dotted with 1, 2, 1. Well, that's just going to be -2 minus 2 plus 1, which is -3. And then, so we don't have any variables in here. We know that the divergence theorem states, sorry, well this really isn't a divergence theorem, but we know that for the flux we need the total, the volume of this cylinder here. And since we can just do that without any actual integration if we know the formula for the volume of a, sorry, not the volume of this, sorry, ignore that, it's late at night. We need the area of the xy plane projection, which is just a circle with radius 1. Because no matter where we are in this cylinder, we're always a circle with radius 1. And the area of a circle with radius 1 is pi r squared, where r is equal to 1, which is pi. And so our answer is -3 pi. Okay, 19, we're evaluating the outward flux in this vector field and in a surface which is closed, sides, top, and bottom. And that's an instant indication that, okay, we should be using the divergence theorem, which states, let's see, yes, which states that del dot f integral dv is, our flux through the surface. So let's find del dot f. Well, del is just going to be d dx, d dy, d dz, whereas f is going to be 3x, 4x, sorry, where f is going to be 3x, 4x squared, y squared. And so if we take our dot product, just going down here, well, the partial derivative of 3x with respect to x is 3, and there's a dot product, so we're adding. The partial derivative of 4x squared with respect to y is 0, and the partial derivative of y squared with respect to z is 0. So overall, our del cross f is just 3. And here is the case where we can just multiply by the volume because we're taking a volume integral. So this is a constant. This would get moved out of the integral. We could do the whole thing, but this is an exam. We're looking for any ways of saving time or checking our work in other ways as possible. So we're dealing with a cylinder, there we go, of radius 1 and height 1. So v equals pi r squared h, where r and h are 1, so volume is pi. And so there we go. We have our 3 pi, where pi is the volume, and 3 is our del dot f. Okay, so if s is part of the paraboloid, blah blah blah, where z is greater than or equal to 0, and we're given f, our normal vector is the upward pointing normal vector, then we're looking for curl f ds. So whenever you see curl f ds, that's an indication that it is time usually for Stokes theorem. So remember, when we're taking a Stokes integral, we need f, and we need to, oh sorry, yeah, we do need curl f. We need curl f, and instead of ds, we need negative zx, negative zy, comma 1, and d a r. There we go. So you can look up why exactly this is this. I am not the one to ask. I just remember it, and we know that we want an upward pointing normal, and this satisfies that with our positive z component. So let's find curl f. Let's find those partial derivatives, and let's get out of here. So curl f is going to be del cross f. So d dx, d dy, d dz, even though those aren't d's, I know, it's automatic, where f is negative y, x, z. So crossing this guy up, we're going to get 0, we're going to get 0, and we're going to get 2. So 0, 0, 2 crossed with, well, it doesn't matter what zx is, doesn't matter what zy is, it doesn't matter because we're dotting those with 0 each. So whatever, whatever, and 1. And that dot product is going to be equal to 2. And in this case, remember with Stokes Theorem, we're dealing with the 2D projected area of our graph. Whereas the Divergence Theorem deals with volume, like we were looking at up there. And so we know that whatever the area, the xy plane area of our shape, of our surface is, multiplied by 2 is going to be our answer. Well, we're looking at the paraboloid z equals 4 minus r squared, and for z is greater than or equal to 0. And so what we can do is just use z equals 0 to find that xy plane projection, which is r squared equals, that's not an r squared equals 4, r equals 2. So we're dealing with a circle of radius 2. And finding that area is pretty easy. Pi r squared is just going to be, where that's equal to a, it's going to be 4 pi multiplied by 2. We get our 8 pi, and yes, sweet. And that is that for this exam. Please let me know if there were any issues with any of the explanations, even if it's just like you went through this too fast. I have no idea what you were saying. Your drawings are terrible. Except don't say that because I already know it. But yeah, I hope this was helpful. Let me know what I can do to improve in the future.